All right, guys. So, how's everyone going? What I'm going to do is I'm going to walk you through the accommodation piece and kind of get some clarifications. A lot of you did a wonderful job explaining it, but I want to make sure that we get all the intricacies of what this is and what it's all about, right? And so, what we're going to do, let me go ahead and share this screen for you real quick because I want to bring up. So, this is the graph that we talked about. So we'll go through that in detail. And then if I come down here, these are some other graphs that I find very important. And they're all the way down here. And so this kind of gives you an idea of what we're talking about here, okay? Let me go back up to this graph. And really, so what this is, right, is this is an idea of what people do and how people are different when it relates to Newton's second and third laws, right? And so Newton's second law is of course, a law of acceleration. It's the sum of forces on in whatever direction is mass times acceleration. And Newton's third law is action-reaction, right? So for every action exerted on A by B, there's an equal and opposite by B onto A. And so what's happening with this is we use Newton's second law to be a predictive model. And if you look at if you follow a normal equation, let me get my annotation skills going, of y equals mx plus b, okay? And then if we do this, and all we need to do is force equals mass times acceleration, right? And so all we're doing here is essentially, we're just removing this constant. And because this constant for us is going to be the 0, it's right there. That's where the y-intercept is at 0. Okay. So what we want to look at is this component here, and really it's going to be a predictive model, right? So we're using mass and acceleration as what we're manipulating. This particular paper manipulates the mass component, right? So they add different masses to different extremities of or different positions, and they have the hands go into different positions. So we've also added mass to a weighted vest. There's many ways you can add mass to individuals during these processes. So that is the one way we manipulate this. And then to manipulate acceleration, the idea with manipulating acceleration typically is that we are going to change the height at which somebody drops. So typically we do this with the drop landing. Or counter movement jump and making sure people are jumping. Because as you get higher, right, your acceleration should increase at the ground because your velocity is increasing by the time you get there, right? So remember what acceleration is. It's that delta V over delta T. This is very important because what we're going to manipulate in this paper in future is this delta T concept. Okay. So let's talk about how this all works into this graph over here. And it's going to start with this concept right here, which is this Newtonian model. And you notice it's a linear model, and that's a predictive model. So we're predicting that if we manipulate the mass or a certain increase it by a certain amount, then we should be able to predict based off this model what the force outcome is because we're expecting the acceleration profile to be the same, okay? Now you're probably saying, well, I don't understand. People are walking. How can you change acceleration? And you manipulate acceleration by how you interact with the ground, right? So if I walk more stiff, what does that do? Well, that increases my acceleration. If I walk more compliant, what does that do? It decreases my acceleration. Wow, Josh, how does it do that? Well, this is how it does it, right? Because remember what I just told you, that acceleration is delta V over delta T. If I become more compliant, what am I doing? I'm increasing the delta T. If I become stiffer, I'm decreasing the delta T. Okay, so it all basically comes down to how long that center of mass has that change in velocity. So say if it's 10 meters per second change, well, if it's over 2 milliseconds versus 10 milliseconds, right? So you can see how that affects the acceleration. So if the acceleration just stayed the same and we added the mass, then we have this Newtonian model that we're going to go under. And that's where you get the Newtonian model. Now, it's human motion, and we all behave differently. So in this graph, you see a couple differences. You see super Newtonian, you see positive biomechanical, fully accommodated, and negative biomechanical. So this is where it gets interesting, is understanding what each of these means, okay? So fully accommodating is simply that with the increase in mass, there is no increase in the force, ground reaction force that they measured, right? So if I have Newton's second law here, and I'm saying that I increase this mass, well, if it was Newtonian, then it would have an increase in force as a relationship to that increase in mass, right? But what we're saying here is with this increase in mass, there is no increase in the force production, right? And so that's a very important piece. And with this, I think it was Ramon. Ramon, you actually, when we go down to this, oh, it's not going to let me move down, scroll down. Let me see if I can scroll down, hold on. Oh, not going to let me do it? Hold on, maybe. There it goes, all right, cool. So Ramon actually spent some time talking about this graph and did a good job with it. And the idea is this, right? So if I was looking at it, and here are your mass increases on this, right? So these are, so 0 Newton increase, which is body weight, okay? And then you have 89 and 44. So what happens is they were measuring the peak ground reaction force. And they measured this first one because this is the lead leg in contact. This area here, the trough, we call that a trough, that's during mid-stance. So an interesting phenomenon happens when you're walking where the center of mass actually is going vertical, going back upwards during this portion. So it's negating that acceleration due to gravity, and therefore you have a little dip in the vertical ground reaction force. And then here, it's when the other foot is hitting the ground and getting loaded while the trail, so this represents the trail leg, while the trail leg is going off, right? So what we're measuring is the greatest ground reaction force and peak at this location, okay? And what you can see is if this is a Newtonian model, then this middle one should be halfway through between the 0 Newton and the greatest, which is the 89 Newton, right? So it should be there if that was a purely Newtonian model. And so we can see that's not. And that's the importance there going forward with that, okay? So let's go back up to our model. So now we know that humans don't really behave like a predictive model. And what happens is structures and materials that aren't human in nature, can't manipulate their body, are pretty much following this Newtonian model, depending on if there's heated and if the material properties change a little bit. But for the most part, they're going to follow this Newtonian model. Okay? So we just talked about fully accommodating, and that's when there's no change in the ground reaction force, vertical, peak vertical, when there is a change in the mass. So even though we have an increase in mass, the person manipulates the body typically through knee flexion or trunk, anterior flexion, hip flexion, ankle dorsiflexion. So those are all the components that are going to make it so they land softer. Sometimes they'll take shorter footsteps, which they're shorten their step length, which also allows that. These are all some different mechanisms, right? So now what we have is we have positive biomechanical and we have the super Newtonian. So both of these, we see an increase in the ground reaction force peak with the increase in mass. The difference is the positive Newtonian is less than the predictive model. The super Newtonian is greater than the predictive model, okay? So remember, the predictive model is F equals ma. For every increase in the mass, we should be able to follow that slope and predict over, right? So if I come up, if the applied stressor, which is on the x-axis. I'll say, okay, I went over here, and here's my 89 newtons. I should be able to come up to that Newtonian model and say, okay, my external ground reaction force, which is the y, and so this is GRF ZP, should be, and I should be able to give you that answer, right? So what we're saying here is that the ground reaction force in the peak of this model in positive biomechanical is going to be less than that predicted, right? So again, if I have, see, if I, this is where I'm supposed to be, and I come up on this dotted line, if I'm here, you see where that is. But because my line becomes this one here, the value on the y, the peak, is less than. Conversely, if I did it in the super Newtonian region, which would be somewhere up here, see how it's greater than, right? So if I went in the super Newtonian, that simply means that my measured ground reaction force during the trial was greater than my predicted Newtonian model, F equals ma. That's super Newtonian. If it was in the positive biomechanical, that means that my actual trial measured peak ground reaction force was less than predicted, but greater than their body weight condition. Okay, that's really important because there has to be something that it's, and that's what this. So that's what this at the very point here, that dot at the very beginning, this is your body weight condition, right? So that's your normal condition. And you get this guy right here is your body weight condition. If I just walked that same velocity down the pathway, which is one of the conditions, 0 newtons, that's body weight, this would be your measured peak ground reaction force. Now, I add the 40, whatever it was, newtons, and there it is. And then here is the 89. So, right, so 44.5, 89. So body weight or 0, 44, 89. That's how we're going to do that, okay? Then the last one we got to talk about is this negative biomechanical. Negative biomechanical is a very interesting phenomenon. It's something you don't see very often, right? So typically you see this when somebody portrays the task as being very demanding. Could be a novel task. It could be you have a history of that task hurting or injury, or you're very cautious. And so what happens is you change your position so much that you actually reduce the ground reaction force from the body weight conditions. And so you don't see it very often, but you do see it, okay? And I'm going to take you down to those graphs, and I want to walk you through the graph down here to show you what that looks like, right? If we look at these graphs now discuss and talk about what it is. So this is body weight condition at 0 to 44.5 newtons, which is the mass they added. This is, they were at for the 44.5, and then they added the 89. And this is 0 to 89. And what you have here is all of these gray ones are individual people, trials. And then you have a mean and standard deviation, or the Newtonian strategy line that is seen from this concept, right? And so if you look at this, you're going to see that a number of these individuals are what we call, so this dotted, the solid black line is the Newtonian line, right? So if these people followed in each one of these, let me put these up here and see if I can get it for you. So if they follow the purely Newtonian, these are the predictive models, okay? And so what you're going to see that in the first one, going from 0 to 44.5, so 0 to the second condition, which is the lesser mass added, these people, what would you classify them as? Above the line is super Newtonian, okay? If I was fully accommodating, let me draw that line for you. The fully accommodating line for all of them would be right there. That's fully accommodating. And you have nobody in that area. Then what you have on the very first one, all these individuals are positive biomechanical, right? So they had an increase over the body weight condition, but it wasn't quite to the level of the Newtonian model. Here is your single negative biomechanical response. That individual reduced their peak ground reaction force in the 44.5 Newton over what they did in their body weight condition. So that's how you see this. Now, what you're going to notice too is over here, this is 44 to 50 to the 89. You have super Newtonian, positive biomechanical, nobody down in the negative biomechanical, nobody at fully accommodating. Over here, super Newtonian, positive biomechanical, none for fully accommodated negative biomechanical. But what you should notice too in this whole process is that you don't see really anybody. Now you can zoom in, I'm sure in this second condition here, this guy here, there's probably somebody pretty close to Newtonian line. There's probably somebody pretty close, but they're not necessarily meaning they're going to do it, right? And so the dotted line of all these, and this is a very important, is the dotted line that you see, black line, those are the mean for the entire group. And the closest mean to the Newtonian is in the first condition, which is the 0 to 44.5 newtons. But as you can see, they're also pretty spread out. And the reason why it's probably the closest is because they're the ones, that's the one condition that has the most spread below and on top. Everybody else has going, most of them up on top, right? So more in the super Newtonian. So what I want you guys to be able to do with this is, what I need you to be able to do with this is look at this graph and explain this graph to me, okay? And how I want that explained is, you need to do a couple different things. You need to be able to explain to me what the X and Y axes are, right? So applied stressor, there's two different applied stressors, an increase in mass or an increase in acceleration. Those are the two applied stressors. You're either changing the mass or the acceleration. So if I tell you that you're doing a drop landing from a higher height, you should understand that I'm messing with the acceleration, okay? The external reaction force is going to be the ground reaction force component, okay? Now, what I need you to be able to do is this. I need you to identify that this dot is the body weight condition. That this line, the Newtonian line, is the predictive model from F equals ma, Newton's second law of acceleration. You should be able to say, if I have an increase in mass or an increase in acceleration set, I can go onto this graph, go up from the increase to the Newtonian model, and then go over, and it should give me the ground reaction force. The other things I need you to be able to do is say, okay, for everybody else that doesn't follow that, you're either in the positive biomechanical, super Newtonian, fully accommodated, negative biomechanical, and you need to be able to explain what those are, okay? No, we didn't talk about, and it's not that important for this class, but this idea of threshold and failure, okay? And so the idea is this, and I don't need you to do this for the thing, but it's a predictive model to talk about the thresholds for failure. So you'll see that there is a limits on each side of the peak force, negative and biomechanical. And what happens is, as we increase our stressor, right, we have more ability in the positive than we do in the negative, right? So if we go too much in the negative, it's a less of a stressor add to cause injury than not, okay? I don't need you to talk about that for this, but I want you to be able to explain the difference between fully accommodating, positive biomechanical, negative biomechanical, fully accommodating, and how those relate to the normal or the control condition, which is in this situation body weight, And the other one, it may just be a drop landing, or it may just be the way we land from a certain height, and how each of these relates to the Newtonian moment. Okay, so I hope that that explains it all for you. And then what I'm going to do is I'll post something on here and try to get it so we can all get together for a review this week as well.